Hello, everyone. Okay, let's get started in just a moment. So I'm just going to share my screen and then we can get started. Okay, so um, I think let's just wait 2 more minutes for anyone else who wants to come in and watch the program, and we'll get started soon. I'm very excited for the session today. We have a lot to talk about. Hi, Miss Soto. I see your message. Thank you. That sounds great. So in just 1 more minute, we'll get started and then we can talk about the brain. Okay, so today I have a bunch of interesting stuff to share with all of you. I'm going to be talking about how we make decisions, how we're able to think, how we're able to, do things that we are able to do as humans, but not as animals. And I'm very excited to talk about the brain today. So before we get into the new stuff, let's talk about a quick review in regards to the different parts of the brain and how exactly the brain works. So here are the different parts of the brain. So the brain is made up of four lobes. If you remember from last time, there's the frontal lobe at the front, the parietal lobe on top, the temporal lobe on the side, and finally, we have the occipital lobe way at the back here. Each of these lobes performs a special function. The frontal lobe at the front of our heads allows us to think about things. So, for example, if we want to play basketball and we want to decide when exactly we want to shoot the ball into the hoop, that's the frontal lobe making that decision. But if we want to listen to something, understand why this train is screeching rather than going by very quietly, the temporal lobe makes that distinction on the side of our head. And that makes sense because it's connected right next to our ears. Then we have the parietal lobe at the top of the brain. And this part is very, very cool and very important because it allows us to feel and touch things. And through that interaction process, we can differentiate between things like slime and things like hard rocks or something like that. So it's really cool to think about what all the brain can do. And the most important part, though, or one of the most developed parts, is the occipital lobe. This is way at the back of our brain here. And it's really interesting to think about all of the things it does, especially given the fact that it's connected to our eyes. And our eyes are able to actually take all the information we see, process it, and bring that to the back of our brain. That's very incredible. And that shows how important our eyes are for processing in our brain. In fact, one cool fact I want to share with you is that if people are blind or they're unable to see things, sometimes the occipital lobe will take over other things like hearing or being able to play the piano or things like that, which is why individuals like Mozart or certain other people are very, very skilled in certain things like music. And we're actually going to be talking about music a bit later as well. Okay, so just to summarize, these are the different parts: the frontal lobe at the front, parietal lobe at the top, the temporal lobe connected next to our ears, the occipital lobe way back here, And finally, we have this mini brain hanging at the bottom, kind of like a small bulge right there. Looks kind of weird if you look at it under a microscope. You've got all sorts of spikes and lines, but this part is very important for allowing us to balance. If we want to shoot a basketball into the hoop and land on both of our feet without tripping and falling, the cerebellum has to make that sort of connection as to when we should land and those type of things. So it's very cool. And then let's talk about the neuron again. So if you recall, the neuron is basically a cell inside of our brain, and it's connected to other neurons like itself in order to communicate and speak with these neurons using electricity. So in this video, if you take a look, basically what's going on is that one neuron emits an electrical signal that goes to another neuron, and in turn, that neuron shares that electrical signal with another one. And by way of transmitting these electrical signals from one neuron to another, the brain can speak not only within the brain and itself, but also with different parts of the body. And that communication, that ability to talk, is what allows us to flex our muscle when we exercise, or to be able to get up from a chair when we want to go outside. Those sort of decisions are what are made in the neurons. And exactly how does the neuron work? Well, it's a very, very complicated process. And there's so much that can go wrong, which explains a vast variety of diseases like Alzheimer's, Parkinson's, even multiple sclerosis, if you've ever heard of that. But essentially, what happens is that inside of the neuron, there's an electrical signal, kind of like that blue pulse that you saw before. And that electricity travels through the neuron. And then at the end of the neuron, it emits tiny chemicals. Those chemicals attach onto the next neuron and trigger a new electrical transport. And through that process of going from electricity to chemicals to electricity again, and so on and so forth, the neurons are able to speak. And that's how our brain speaks with the rest of our body. So this brings me to one of our coolest parts, reasoning. How do we make a decision? Let me tell you this. It is so complicated, but it is really, really interesting to think about how it happens. I'll tell you that there are two parts that we should know about. The first is the prefrontal cortex, and the second is the amygdala. So the prefrontal cortex is found at the front of our brain. The amygdala is a tiny bulge that is found on the inside. So I'm going to be talking about the connection of those two. But before that, I want to show you a really cool video. So this is called the Marshmallow Test. Essentially, the idea of this is that kids are given a marshmallow, and then they're asked to not eat the marshmallow until the person who gave the marshmallow returns back to the room and gives them another one. If they do eat the marshmallow before that person returns, then the kids cannot get another marshmallow. But as I'm sure you can imagine, these kids love marshmallows and they want to eat it so badly, which is why it's very hard for them to control their instincts and, wait for the person to come back. So let's take a look at this video and what happens.
Okay, sit in that chair. All right, here's the deal. Marshmallow for you. You can either wait, and I'll give you another one if you wait, or you could eat it now. When I come back, I'll give you another one, so then you'll have two. But stay in here and stay in the chair till I come back, okay? All right. I'm gonna go do something and then I'll come back.
It smells yummy. It smells really good.
So as you can tell, he's starting to pick at it. and she is too. It's really hard to handle the temptation, but let's
All right, it's
fast
up to you. You can
forward
have
and
it now, or
see.
you can wait.
Eventually, most of them end up eating it, kind of like that. So as you can tell, it's really hard for them to resist eating it. I mean, the marshmallow's right there and there's nothing else to do. So might as well just eat the marshmallow, right? But why is it
Okay,
that it's
signature.
so hard to wait? Well, the answer is it's our brain, just like everything. In our brain, we have this tiny bulge in front called the amygdala. If you see the white bulge right there, that amygdala is like the scaredy cat of the brain. The moment anything happens, the amygdala becomes super scared. It's kind of like, why is this happening? What can we do to save ourselves? Kind of like an animal, right? Whenever an animal does something, they do it in order to survive. That's what our amygdala tells us. When we're hungry, we need to eat. Otherwise, bad things are going to happen. Our amygdala makes those decisions. So, in order to counteract that effect, we have something called the prefrontal cortex. The prefrontal cortex is found in the front of our brain. And it tells the amygdala, buddy, calm down. We don't worry about it. Um, Whatever happens, we have to think about what to do based on smart decisions rather than quick ones, right? So, for example, in this marshmallow thing, the amygdala was telling the kids that I'm really hungry, I have nothing to do, I want to eat the marshmallow super badly. But the prefrontal cortex at the front of the brain was trying to tell the amygdala that no, just wait. It doesn't make sense for you to eat the marshmallow right now, because if you wait, you might get another one in the future as well. So, that battle between the two of them is what allows us to make our decisions for essentially everything. And this is what I want to talk about: the amygdala versus the prefrontal cortex. So here's the first round. What exactly would happen, right? There's a scary bee. The amygdala tells us, run, go away, the bee will sting us. We have to get out of here as quick as possible. The prefrontal cortex says, let's stand still and not move. So take a second to think about this. What do you think? Who do you think will make the smarter decision? The prefrontal cortex or the amygdala? So it seems that we can sort of agree that it probably will be the prefrontal cortex, because the prefrontal cortex is the one making the smart decisions. So 1 point goes to prefrontal cortex. Second round, fire. Oh no, suddenly there's a fire. The amygdala says, let's run, let's get out of here. It's very scary. The prefrontal cortex says, no, wait, we need to come up with a plan to try to figure our way out of this fire. In this case, who do you think will win? Should we just run away? Should we come up with a plan? Who do you think would win, the amygdala or the prefrontal cortex? All right, so I think the answer is the amygdala in this case. Because if we don't get out of there super fast, then that might actually be very harmful for us. So we need to sort of counteract the prefrontal cortex that's telling us to wait and just get out of there, or else there can be really, really bad things that happen. So we need to hurry up. And that's what the amygdala tells us to do. So therefore, there's a tie between them right now. The amygdala won, the prefrontal cortex won. So we need a tiebreaker. There's an important test tomorrow. The amygdala, it loves things that will make it happy. So it wants to play video games. But the prefrontal cortex says, let's study, right? If we don't study, we might fail the exam and bad things might happen. So in this case, I think we all can agree the prefrontal cortex will probably win. And therefore, it seems the prefrontal cortex won this battle. But that means also the amygdala sometimes has a very, very important role to play. Otherwise, it would not be there, right? What would be the point of it? And it turns out that in people like serial killers, the amygdala is very, very small. because they don't feel scared of the crimes or actions that they take. And as a result, scientists have actually measured the size of their amygdala and the connection to the prefrontal cortex. And they see that the prefrontal cortex is making all the decisions for them. It's determining exactly how to go about things. And therefore, the amygdala is not there anymore to feel bad about it. And that can result in some pretty bad consequences too. So we need both of them, and we need both of them to talk to each other. Otherwise, it can be very difficult for our brain to figure out what is the best decision for us to make. And that brings us to our next activity, which is judge the brain. So I have different situations, and we're basically going to discuss what we should do in every situation together. So imagine this is the first case, bullying. So we see someone making fun of another student by calling them names and teasing them. You can tell that the person is being bullied and feeling very sad. Many kids next to the bully are laughing along. And this is a very unfortunate situation that might actually happen in a school setting. So, what would our amygdala tell us to do? Remember, the amygdala is the scaredy cat center. So, I think based on that, the amygdala would tell us to be scared and not do anything. Because if we do something, our amygdala would tell us that maybe we won't be friends with the person anymore, or maybe the bully will start bullying us instead, or something like that. But the prefrontal cortex tries to override that and say, if you don't help the person, then maybe that person will be in extreme trouble and experience extreme sadness and anxiety in the future, which will be very bad for that person. So the prefrontal cortex might tell us to take action. And therefore, there's a battle between those two. What should we do? Should we do nothing, or should we actually confront the bully directly? This is a very confusing situation. The answer is that we'll probably come to some sort of compromise in between. We won't confront the bully, but we also won't do anything as well. We will probably go to a teacher or the principal or someone and tell them anonymously that, I saw this person was bullying this person. Can you please address the issue and do something about it? Because I'm very scared for the person who was being bullied. And coming to that sort of compromise is very, very important between these two structures. Next question, bake sale. So you're planning a bake sale event in your school with other students in your class. However, while planning the event, two of your classmates seem to always be arguing, making it hard for all of you to come up with a plan. As the leader, you have to decide how to resolve the situation. So that brings us to the second dilemma. What will the amygdala say? Amygdala, once again, scaredy cat. It wants to stay out of all of this. It will say that let them handle it on their own because I'm too scared to get involved because they might get mad at me and scream at me or something. I'll do something wrong. The amygdala is super scared of that. The prefrontal cortex, on the other hand, is saying that, you know what? I don't think that's right. As a leader, I have to take action and figure out a solution here. So the prefrontal cortex and the amygdala, once again, we have that battle going on. And we'll come to some sort of compromise, once again, most likely, where we'll sit with the two of them and discuss with them what their ideas are and what they're feeling and why they're arguing with each other in order to understand each of their perspectives and come to a sort of compromise. So being able to act as a leader requires us to understand our own fears through the amygdala and connect that with the prefrontal cortex to override that fear. All right, third case, birthday party. Our friend invites us to a pool party over the weekend. Although the COVID-19 quarantine is still in place, most of our friends are still going. Now, this one's a very tricky situation because the amygdala might scare us in many different ways, not just in one way. Our amygdala might say, I'm very scared to go to this pool party because I might get COVID. Or it might say, I'm very scared of not going to this pool party because if I don't go and all of my friends are going, maybe they won't be friends with me anymore. So within the amygdala itself, we have a battle. What will we do? The prefrontal cortex comes in as a regulator of that and says, okay, you're right, amygdala. There's pros and there's cons. And what would you risk? Would you want to get COVID but keep your friends? Or would you risk maybe not keeping your friends, which probably won't happen in the first place because they'll understand why you're not going, and risk and therefore make sure that you're not getting COVID. And regulating that battle, the prefrontal cortex will come up with the final decision and allow us to say that, yes, we're going to go to this party, but we're going to take certain precautions, or we're not going to go to this party because we just don't deem that it's safe right now. So that sort of decision making process is very important in this sort of situation. And that sort of tells us that the amygdala itself might have a conflict within itself. The prefrontal cortex is there as a regulator. And finally, we have the fourth case, which is our best friend cheating. So you see your best friend cheating on a test with the help of the student that they're sitting next to. What would the amygdala tell you to do? Quite simply, the amygdala might say that we're very scared of reporting our friend because then that friend might get in trouble and they won't be friends with us anymore. Or it might go the other way, and you might feel scared that if I don't report the cheating and then the teacher catches me as not having reported it, maybe I'll be in trouble instead, or something like that. So the brain is very complicated. Everybody thinks very differently. The amygdala and the prefrontal cortex will each have their own way of addressing it, which explains why people will behave differently based on these different situations. But it's important to think about how we can overcome that. My main goal in explaining these situations is for you to realize that there are situations where you might be scared. But if you understand that the amygdala is the reason why you're feeling that way, and ultimately it's the prefrontal cortex that should make the decision, you might be able to realize that you should weigh the pros and cons of every decision you make before making it. And as a result, you can make decisions which are very smart for you and for the people around you. So this answer to this question, there's no set answer. Maybe you go to your friend directly and tell them it's not good for you to be cheating in this way. In the future you might get caught in some place, right? Explaining to them the consequences, or you decide that I'm going to take it up with the teacher, but I would ask her not to take like some extreme action against my friend. Otherwise, they're not going to be friends with me anymore, or something of that sort. So, coming up with a smart decision like that, that's ultimately the goal that all of us should be striving for. Okay, and this brings us to my next module, which is music. So, our brain, if you remember, it's basically very inclined to listen to things, especially our temporal lobe. The temporal lobe is connected right next to our ears. If you remember, it is the one that allows us to process the things that we hear. We can differentiate a screeching train noise from someone speaking to us very softly in a whisper because of the temporal lobe. And it turns out that the temporal lobe has a great connection to the stuff inside the brain too. Because if you take a look at the temporal lobe, it's right here. And as you can see, it's very close to all of this stuff in the interior. One of these structures right here is called the hippocampus. Sounds really weird, right? It has hippo in its name. But essentially, the hippocampus right here, the white line at the top, that is very, very important for us to be able to remember things. So whenever we listen to a song and we want to hear it and we want to store it in our memory, right? If we get something like an earworm, we're stuck with that song for a long time. That gets processed in the hippocampus. And that's because it's connected right next to the temporal lobe. Therefore, scientists have also seen that our brain becomes very happy when we listen to certain songs. It helps us when we're studying with remembering things, especially songs that we like. If there's a song that someone who's really old listens to from their childhood, we can see that a lot of patients with things like dementia, which causes memory loss, a lot of them do not feel as inclined to memory loss anymore. It's a very therapeutic way for them to overcome certain medical conditions. Therefore, music is a great way to overcome these sort of emotions and feelings. Or in our case, trials and tribulations. So now I'm going to play a game. So I want you to see how many things you can remember. All right. So I'm going to first start off with showing you a few different objects without any music. And I want you to try to remember as many objects as you can. And in the chat, type out how many objects you remember. All right. So here we go. 3, 2, 1. Without music. All right, so type your answers in the chat. I would love to see how many objects you think you remember. Um, and then now let's play with music and let's see which one you think you remember more for. So I'm gonna turn on a musical melody. All right, so type your answer in the chat. Let me know how many um, uh, objects you think you remember. I would love to see if you got more for the music or the one without the music. So um, let's see. Okay, awesome. And then we're gonna go back to it at the end and I'll just check the answers. Let's talk about distractions next. So, music is really interesting because it connects our our temporal lobe to the inside of our brain, right? As I mentioned earlier, the the hippocampus, which has all of these special neurons, which converts our memories into short-term memories, the way that gets converted into something we remember for a long time is a very interesting process. First, when we take a look at something, let's say we take a look at, the name of a restaurant, and we want to remember the name of that restaurant the next day because we plan to go there with some friends. What happens is that the moment we see that restaurant's name, that gets converted to our vision, and our vision takes that to the occipital lobe way at the back here, right? Remember the occipital lobe? But one part of that also goes to the hippocampus. The hippocampus takes that information and converts that into a memory, but the hippocampus cannot convert that into a long-term memory. So we might remember it for a few moments and then forget about it. In order to take that and convert it into a long-term memory, the hippocampus, if we're constantly exposed to that name over and over again, we constantly see the name of the restaurant, eventually there will be a connection that forms between the hippocampus and the outer cortex of the brain, the spaghetti-like structure right here. That connection allows us to remember things, and it's stored, therefore, in our cortex. All of these folds are very special because they basically hold all of our memories. And therefore, a long-term memory is very, very interesting to form because it can actually allow us to integrate it into our brain in this anatomical manner. So it's very interesting to think about how this works. But when do distractions come in? Well, when we have multiple things in our brain at the same time. So our hippocampus gets input from our vision. It gets input from our ears. It gets input from our tastes. We're watching something while we're eating, while we're also listening to what we're watching, right? There are a bunch of things going on, and our hippocampus has so many things it has to remember that it gets confused as to what it should pay attention to. Therefore, if I don't know if you notice this, but when we eat something while we watch TV, maybe it doesn't taste as good as when we eat it without watching anything. And that's because our hippocampus is very selective in what we pay attention to, the movie rather than our taste. So that's where distractions come in. The senses that we have, we want to present them one at a time in order to understand them. So let's take a look at this video right here. All right, so what did you notice? Type in the chat whatever you think you noticed the most. I'm guessing that your response will be a car. So the car is really, really interesting because it's the only thing in the whole video that's moving. And that shows how our brain likes to focus on particular things while ignoring other ones. There was a sun there. There was even a bridge. There was the grass. There was the blue sky, but none of those things were moving. So most likely our attention, our eyes focused onto that car and ignored everything else in the background. That just shows how we like to focus on particular things rather than others. And why does that happen? Well, in order to understand that, we need to understand brain waves. What? Brain waves? What does that mean? Well, brain waves are special signals in our brain that indicate to us what we are thinking. Now, before it sounds something like mind control or something of that nature, let me show you how it exactly works. So, if you remember, our brain is made up of a bunch of neurons, and these neurons run on electricity. So when a bunch of these neurons fire at the same time, there's a lot of electricity in our brain. And it turns out that scientists in a particular moment can determine how many neurons are firing or how much electricity our brain is creating and measure that through a device called EEG. And EEG, when it tracks in every single moment how many neurons are firing, it creates a sort of wave-like pattern. So in this video, imagine that the brain being pink represents a lot of neurons firing at the same time. So let's take a look at this video when it loads. Okay, so when a bunch of neurons fire at the same time, the EEG scan reads a signal. But when there's not that much firing anymore, it drops back down. And that sort of wave-like pattern, that's what we call a brain wave. It turns out that wave-like pattern is different depending on whether we're watching something, whether we're eating something, whether we're listening to something, no matter what we're doing. The brainwave pattern is really, really cool and really interesting. So imagine we take a bunch of people, put them into a theater, and ask them to watch an action movie. We take the same group of people afterwards, put them into a theater, and ask them to watch a documentary. I'm sure you can imagine that the action movie is much cooler than the documentary. Although some people who are very much into history and stuff like that might think the other way around. But almost 70% of the people in the action movie, based on research, will share the exact same brainwave patterns. Isn't that so cool? The same firing pattern in our brains will be the same pattern for almost everyone in that movie theater at the same time. That really shows that our brain can be hijacked by the directors of the movie into focusing into particular things like the car flipping around the bridge or something else, right? The directors of the movie are really good at focusing our attention on particular things. Meanwhile, in a documentary, only 5% of us will share the same brainwave patterns. And that's because most of us are bored. Some of us might be thinking about what's for dinner. Some of us might be thinking about, what are we going to do next? after the documentary. And therefore, because we're not thinking the same things anymore, our brainwave patterns are also different. So our brainwaves can give us really good insight into what exactly we're thinking about, what we're focusing on in that specific moment, which is why it's such a powerful tool. And it becomes much more important when we think about certain medical conditions like ADHD. I'm not sure if you're familiar with this condition, but essentially, the idea is that in our brain, we have a bunch of, a bunch of signals that are going from our prefrontal cortex, which, if you remember, was the one regulating the amygdala. Between that and the amygdala, there's a huge connection there. And it turns out that in individuals who have ADHD, the prefrontal cortex is much smaller and much less useful for them, which is why it's very hard for them to regulate their amygdala. And therefore, to no fault of their own, it's very common to see individuals with ADHD be very hyper and very, jumpy and going around about, even though there might be a situation like a classroom where they're supposed to sit down and learn. To no fault of their own, it's very hard for them to do that because the prefrontal cortex is much smaller for them. And consequently, we can also see in EEG scans that the activity in the brain in the front is much smaller as well, is much less or much reduced because there's a lot less going on when they're making decisions because of their medical condition. But this does not just have to be the case for people with medical conditions. This can be the case for ordinary people who do not have medical conditions as well. We're hooked onto our phones these days. Things like addiction through smoking or drugs or stuff like that can be very detrimental to us as well. And that all goes to show how our brain can really, really be manipulated in order to focus on particular things and ignore other ones. And that's basically one very unfortunate part of our reality and our situation. The fact that we have to control how exactly we think about going about our behaviors. Oftentimes, it's very, very easy for us to fall into particular traps like addiction and things like that. Overcoming that requires us to use our prefrontal cortex. That's my message to you today as well, that we should think smart and act smart. Whenever we make a decision, we should think about what in our brain is making that decision. When we decide that we want to go, when we want to go to our friend's house, something as simple as that, we want to think about what the amygdala is saying. What is the prefrontal cortex saying? What is the better decision between those two opinions? And through that process, if you are able to bring that habit into your life, if you're able to make that sort of balanced decision, then maybe in the future that will help us a lot, because that will allow us to make decisions that are very, very beneficial to us rather than being rushed and impulsive. And consequently, our thoughts predict our behaviors. So therefore, we can act very smart as well based on how we think. So that is all I have for today. But before we before we conclude, I just wanted to see the responses for the number of objects that you guys saw. So it seems that there were more objects that we saw before than we did afterwards in the music thing. And that's very interesting to see, because it seems that for most people, music often helps them with studying. But maybe in this case, the fact that we're listening to a completely new song that we were unaware about um, allowed us to see something new. And that caused us to be distracted rather than enhanced in our presentation. So thank you so much for coming. It was great to speak with all of you. If you're interested in learning more about the brain, you can check out my website, thebrainbunch.com. And also, if you're a kid in school, we would love to hear your thoughts about the brain. Come and join us, write a blog for the Brain Bunch. If you're interested, let me know, and we can certainly talk about this in the future. Thank you, and have a great day. And thank you for all of your lovely comments. It was great to host this presentation with all of you. Bye.